This is a really quick video introducing the concept of the derivative. The derivative of a function is an equation that allows you to find the gradient of a function at any point. So it's all about gradients for now. Later on it becomes about more important things than just gradients, but for now that's what we're going to cover. So let's talk for a moment about gradients. Let me sketch a quick graph here, something that looks like this. Let's say that this is the graph of y is equal to 2x plus 1. What's the gradient of this line? Well, we know from high school maths that the gradient of this line is going to be 2. I'm going to write that as m is equal to 2. And it's 2 there at that point, and it's 2 there at that point, and it's 2 there at that point. So our gradient is constant, and it's positive the whole place. Let's look at another line. Let's say that we've got a line that looks like that, and we'll say that this line is y is equal to negative x plus 4. What's the gradient of this line? We know that for this line the gradient is equal to negative 1, and it's negative 1 there and there and there and there, negative 1 the entire line. All right, now if we have a look at another graph, let me quickly sketch something from our function study unit earlier. This one here is the graph of y is equal to x squared. Now it should be immediately obvious that this graph doesn't have a constant gradient. We might think about the gradient there. What's the steepness of that point? It's obviously going to be different to the steepness there, or the steepness there, or even the steepness there, because a parabola gets steeper every single change in x value. So we can't just say this is the gradient of the graph, because the graph has a different gradient at each point. So how do we work out what it is at any of those points? Well, we actually have an equation, and that equation we're going to call the derivative. I'm going to tell you how we come up with the derivative later on, how we find it, but for now just take my word for it that the derivative of this function is 2x. We write our derivative using this symbol, dy dx. You might be interested to know that where that comes from is that it was the old symbol delta y over delta x, where delta is our scientific term for the change in y. What's the change in y? Well, the change in y is how much our graph goes up, that dotted line there, versus how much it goes across that single line there. So this is basically another way of writing rise over run. So rise over run is how we teach it in high school now, but rise is really our change in y divided by run, which is our change in x, delta y over delta x, and a more modern way of writing delta y and delta x is just dy dx. So that's why we use this dy dx notation. It really just means the gradient. Now, later on, we're going to change that dy dx, so you might have different variables there, or the double derivative. We'll talk about a whole bunch of different things to this dy dx, but for now you just write it as a fraction, and we pronounce that dy dx. You could say dy over dx, but you don't need to. Quite often it's just dy dx. And so in this particular case, dy dx is equal to 2x. What does that mean? Well, this is an equation that allows us to work out the gradient at any point. Let's go back up here and have a look at our y is equal to x squared. Let's say that this point here has an x value of 2. We know that it's going to have a y value of 2 squared, which is 4. Another question might be, what's the gradient at that point? What's the steepness of the graph at that point? Well, what we're going to do, instead of plugging our x value into there, which would tell us what our y value is, we're instead going to plug our x value into there, which is going to tell us our gradient. Now, in this particular case, it gives us the same. That's 2 times 2, so the gradient at that point is also 4. So it's going through that particular point with a steepness of 4 units up for every 1 unit across. Let's have a look at this point here, which might be the point 4 comma something. What's the something? 4 comma 16, because we're plugging 4 into x squared. What's the gradient at that point? We know at that point our derivative dy dx throughout the entire function is 2x, so I'm going to plug 4 into that and get an answer of 8. So even though this goes through the point 4 comma 16, it has a gradient of 8 when it does so. Really quickly, we're also going to talk about positive and negative gradients as well. Looking at this graph, x squared graph, it should be obvious that here the gradient is, the graph is going upwards. As we travel from left to right, it's also going upwards. That's what we call a positive gradient. And so it makes sense to say, in this case, to say that dy dx is positive. What's a shorthand way of writing positive? Greater than 0. So dy dx is greater than 0 whenever x is greater than 0. We also know that our gradient is going to be negative here whenever our x value is negative. So for this particular graph, dy dx is less than 0, which is a nice formal way of saying negative, whenever x is less than 0. What about if it's not greater than 0 or less than 0? Well, the only possible way that can happen is if it is right here. That is our 0 point. And we should be obvious that dy dx is equal to 0 when x is 0. Now, what does this mean? We know from high school maths that a gradient of 0 is a line that is perfectly horizontal. So if we sketch the line y is equal to 3, that line there has a gradient of 0. And sure enough, that's what happens right here. As our curve comes down and touches, we have a point where our gradient is 0. Before I go any further, I'm going to talk about notation. So far, I've introduced you to dy dx as some specific derivative notation. And we use that notation wherever our original function is presented as y equals. So if our original function y is equal to x cubed, then it makes sense to say dy dx and derivative is equal to 3x squared. Again, I'm going to talk about how we get those numbers a little bit later. But if our original function isn't presented as a y equals equation, but rather an f of x equation, we have different notation. So if f of x is equal to x cubed, I'm not going to say dy dx is equal to 3x squared. I'm going to say f dash x is equal to 3x squared. This f dash x means the derivative. So when we're writing the derivative, we just have to be careful to use the right notation. Sometimes we use f dash x, sometimes we use dy dx. Whichever one we use depends on how our original function is presented. So we just make sure that we're using the right sort of notation. It should also be obvious, this is using our function notation system, and you already know how to use that. If I told you that f of x is equal to x cubed, what is f of 2? That means let's plug 2 into our equation. 2 cubed is 8. You can also now pretty easily guess, what does f dash 2 mean? F dash 2 means what's the derivative at that point. And to work that out, we first work out the derivative and then plug 2 into it. So now I'm plugging 2 into 3x squared, and that's obviously 4 times 3, which gives me an answer of 12. All right, so at that point 2, 8, what we know about the graph, without even thinking about the shape or anything else, what we know about the graph is that there is a point here that is at 2, 8, and at that point we have a gradient that is going up at a rate of 12 units up for every 1 unit across. All right, the next step that we're going to talk about is how do we find the derivative? There are some complex ways of doing it, but I'm going to show you the really simple shortcut way. It's not considered mathematically rigorous, and later on we're going to work out a really good, proper way of doing it. But for now, let's just show you what I call the shortcut method. The shortcut method is quite simply bring the power down. So we're going to bring whatever is the power of x, bring the power of x down, multiply by what's there already. And the next thing we're going to do is subtract 1 from the power and put it back. Those are the two things you do. It's pretty simple. Let's do it with some simple cases, the ones I've already done, like y is equal to x squared. We're going to bring down the power. So the power in this case is 2. I'm going to bring that down and multiply it by whatever's there. Well, at the moment there's a 1 there as the coefficient of x squared. We know that every time we see x squared, there's really a 1x squared there. So I'm going to multiply that 1 by 2, and I get, when I'm finding the derivative, and I get 2 times the x, and I have to subtract 1 from the power, which means 2 take 1 is 1, and I put it back, and that's the same as 2x. It's nice and simple. Let's have a look at f of x is equal to x cubed. In this case, I'm going to bring down the power, bring that 3 down the front, and so f dash x is equal to 3 lots of x, and then we subtract 1 from the power. 3 take 1 is 2, so I put that back up the top. All right. What do I mean by multiply what's already there? So far there hasn't been a coefficient. Let's have a think about what the derivative of y is equal to 3x to the power of 7 might be. Well, I bring my 7 down, multiply it by the 3 that's there already. So I'm finding dy dx in this case is equal to 21x, and I subtract 1 from the power, x to the power of 6. It's pretty simple. So simple that I'm not even going to ask you to do some exercises yet. What happens if we've got multiple functions added together? Let's say that we've got a function of x called f of x, which is really just two other functions added together, g of x and h of x. All right. An example of this might be, let's say that our function is equal to 7x squared plus 3x cubed. Now, how do we find the derivative of this? One rule that you need to know is that the derivative of any function like this is just equal to the derivative of the two separate functions added together as well. So when we've got multiple functions that are joined together with addition or with subtraction, then we really just find the derivative of them separately. So in this case, if f of x is that function I've given there, then f dash x is going to be equal to 14x plus 9x squared. I've just found the derivative of each term separately, found the derivative of that one, put it there, found the derivative of that one, put it there, joined them with a plus because that was what there was there before. Let's have a look at another example of that. If y is equal to 7x to the power of 3 minus 5x to the 4, so dy dx using the correct notation is going to be equal to 21x squared minus 20x to the power of 3. So that's how to find the derivative when we've got a coefficient and a power. What if the power is missing, or an even simpler case? Let's have a look at how do we find the derivative of 7x? Well, there's two ways to think about it. One of which is to remember that, well, we know what the line y is equal to 7x looks like. It looks like that, where we have a gradient of 7 the entire time. So dy dx is equal to 7. That's one way of thinking of it. But also we can imagine, well, really 7x is 7x to the power of 1. If we apply our rule, we bring 1 down, multiply by 7. 1 times 7 is 7. And then we subtract 1 from the power, and we get 7x to the power of 0. And we know that x to the power of 0 is 1. So this is 7 times 1, which is 7. So mathematically, we get the same answer as well. What if we're finding the derivative of a constant? Y is equal to 3. What's our derivative? Well, from our graphical method, we know that y is equal to 3 looks like that, which has a derivative of 0. And applying our rule, we know that this is really 3x to the power of 0. If we bring down our 0, we're getting 3 times 0, which is 0. And so 0 times something, we don't really have to worry about what goes there because we've got a 0 out the front. 0 times anything is 0. So we just get an answer of 0. Combining all that, we should now be able to easily find the derivative of y is equal to 3x squared plus 7x minus 4 dy dx. What's the derivative of this function? This is going to be equal to 6x plus 7 and then minus 0. We just don't even have to write it. So that's where I leave my answer. One more thing before I leave you. I've shown you explicitly that when we're finding the derivative of functions that are added or subtracted, then we can just find the derivatives of each one separately. I want to make it very clear that that doesn't work if we're multiplying. If we've got something like y is equal to 2x squared plus 3, lots of x squared minus 5x, it's not going to work to say, oh, well, I'm just going to find the derivative of this first one, which is 4x, and then the derivative of the second one, which is 2x minus 5, and then multiply them together and get an answer of 8x squared minus 20x. That is not going to work. That's not going to be the correct derivative. Same goes for division. We've got another function, y is equal to 2x squared plus 4 divided by x squared minus 1. We cannot simply do the derivative of the top divided by the derivative of the bottom. What we have to do instead in those cases is simplify beforehand. So if we've got something like this presented that way, we're going to have to multiply those two brackets using the box method or some other method to expand brackets to get each term individually and then find the derivative. If it's presented as a fraction like that, we're going to have to cancel out terms, do whatever we need to do to simplify our fraction to get it into something that is just a function we can find the derivative plus or minus another function we can find the derivative of. If necessary, plus or minus another function we can find the derivative of. It only works if these things are joined with a plus or a minus, not with a times or a divide. All right, so that's enough information for you to take away and practice.